Welcome to Recitation number 2, Chapter 2. Today we're going to talk about the structure of the atom. We're going to talk about the average atomic mass, charge and subatomic particles, metals, nonmetals, and metalloids, grams, moles, and atom conversions. The 4 problems you are required to upload on Canvas are problems 2-1, 2-4, 2-5, and 2-8. So let's just start going. Okay, the structure of the atom. So if you get your periodic table out, which you should have every time you're working these, you'll see that we'll pick an element here. We'll pick beryllium. And beryllium has a 4 there, and then the word beryllium. And then you have 9.012. Okay, so this is the name. Actually, beryllium. Your symbol is Be. And it's important here, this is your atomic number. Number 4 is your atomic number. That's kind of like your identity. It's like your social security number. It's like your UK identity number. 4 is the number of protons in the nucleus. So that means that beryllium has 4 protons in the nucleus. If you change the number of protons to, let's say, 5, then you have the element boron. If you change it to 6, you have carbon. So you do not change the number of protons. If you change the number of protons, you have changed the name and the symbol of the element. And then we have different isotopes. Isotopes depend on the number of neutrons in the nucleus. So this is in the nucleus. So if you have like beryllium-9, beryllium-9, then since you have 4 protons, because beryllium always has 4 protons, then the formula would be neutrons plus protons equals the mass. You need to memorize that. And that's the mass, and the mass is always the mass in the nucleus. So the number of protons for beryllium is always 4, and therefore, if you have 4 protons and your mass is 9, then 9 minus 4 is 5. Beryllium-9 would have 5 neutrons. And neutrons have no charge. And then the electrons would be on the outside of the atom. So in this case, if we want a neutral molecule, because if we have 4 protons and they have plus charge, then if we want a neutral molecule, the charge, then we have to have 4 electrons. Electrons do not bring any mass. It's called negligible. So we're just going to put 4 electrons on the outside. And later on you'll learn exactly where these electrons are located. Okay, so that's the structure of the atom. So let's read our question. Indicate whether each of the following statements about the nucleus of the atom is true or false. Okay, so we're going to decide if these are true or false. The nucleus of the atom is neutral. Well, that would definitely be false, right? Because we just showed you that the nucleus has only neutrons plus protons. This is your mass. This equals your mass. This is in your nucleus. Neutrons are neutral, no charge. Protons are positive. So the nucleus of the atom would be positive. The nucleus of the atom contains only neutrons. Well, this would be false as well, right? Because the nucleus contains neutrons and protons. The number of nucleons, nucleon is a proton or a neutron, okay, a nucleon. The number of nucleons present in the nucleus is equal to the number of electrons present outside the nucleus. This is false, okay? Because that would be only if it's neutral, okay? So number 3 would be only if it's a neutral atom would protons equal electrons. The number 4, the nucleus accounts for almost all the volume of the atom. That's not true, okay? So if you listen to your lecture, you'll hear Dr. Haller talk about the nucleus, which has the neutrons and the protons, is about the size of a marble. And then outside, so if you can imagine the Commonwealth Stadium, if this was the 50-yard line of the Commonwealth Stadium, your electrons are actually outside the stadium. Okay? So the volume is really this empty space here. So number 4, the nucleus accounts for almost all the volume, very little bit of the volume. So this is false. Number 5, the nucleus accounts for almost all the mass. That is true. True, true, true. Okay? So let's highlight that one. That is true. True. Number 5, true. Because of this equation here that I told you need to memorize. Neutron plus proton equals mass. And number 6, the nucleus can be positively or negatively charged depending on the identity of the atom. That is the nucleus. That is false. The nucleus can only be positively charged. The nucleus can never, this right here, the nucleus, only has neutrons and protons. We drew a picture here. Neutrons and protons. The nucleus can only be positive. For this problem, suppose there are 2 known compounds containing the generic elements X and Y. You have 1.00 gram a sample of each compound. One compound contains 0.34 grams of X and the other contains 0.44 grams of X. And so you want to come up with a possible formula for these compounds. So when you're working this problem, this is, notice it's a binary compound. Okay, so the first thing you want to do is you want to figure out what your subscripts are going to be. X and Y is your compound, and you want to know what are these little subscripts going to be. And you have compound 1, and then you have compound 2. So the best way to do this is to solve for, the first thing you want to do is solve for Y. So basically X plus Y equals 1.00. And you're given X. So let's do compound 1 first. You have 0.34 grams for compound X. You don't know Y, and they equal 1.0000. So to solve for y, you get y equals 0.66 grams. So if you were to write this now, you would write x 0.34, little subscript, y 0.66. Now, that should look awkward to you because you don't normally see fractions in the exponent in the subscript area. So the second thing you're going to do is you're going to divide by the lowest subscript. So when you divide by the lowest subscript number, you're basically saying x 0.34 divided by 0.34, and then y 0.66 divided by 0.34. This will give you x 1 and y 1.9. 1.9 is essentially 2. So you have x 1 and y 2. Do we see an x1 and y2 for A, B, and C? I do not. So what you can do is you can multiply the same number through. So what if you multiplied the subscripts by 2? If you did that, then your answer would be x2, y4. So for compound number 1, do we see an x2, y4? We do. So we see that one right there. So let's go ahead and solve for the compound number 2. So in compound number 2, we have 0.44 grams of x. So let's do this one down here. We have x 0.44, and if you solve for y, you'll get y equals 0.56. So you do the same thing. 1 minus 0.44 gives you 0.56. Now we divide by the lowest subscript, so each one's going to be divided by 0.44 because we want to get the fractions out of the subscript. So that's x1, and then this is y 1.3. Well, we can't have 1.3, so we're going to multiply a number through both. And so if you multiply this number, you can multiply by 2, and you'll see that that gives you like 2.6. It's not close enough. But what if we multiply by 3? This works out to be x 1 times 3 is 3, and y 3 times 1.3 is 4. And so if you go back up here and you look at, we already said that x2, y4 is good for compound 1. And as you can see, x3, y4 is good for compound 2. So the answer is B. This is recitation problem chapter 2, question 3. And the question is, give the nuclear symbol, isotope symbol, for the isotope of bromine that contains 46 neutrons. Okay, so we're talking about bromine, and you need to know that chemical symbol element is Br. And when you look at the periodic table, you can see that bromine has 35 protons. So to, when you look here, this is pretty much the way it is, the notation. You have your chemical symbol here, which is X. You have the mass number, which is A, and you have an atomic number, which is Z. So in this case, you would have bromine, the mass. In this case, you're going to solve for the mass, and the number of protons, atomic number, is going to be 35. Now, I told you earlier that you need to memorize neutrons plus protons equals your mass. And the number of neutrons change, and this difference in different numbers of neutrons make up different isotopes because they'll have different masses. So the nuclear symbol for bromine, what you need to figure out is, what is the mass? What is the A number, the mass of this isotope? So using your formula of neutrons plus protons equals mass, you can put, you're going to solve for neutrons. You know how many protons because bromine. You know it's bromine. They tell you it's bromine. Bromine always, always, always has 35 protons. And so the mass here, they tell you neutrons, don't they? Look at that. 46 neutrons. So 46 neutrons plus 35 equals 81. Okay, so that's your mass. And the way this is normally written is Br-81. And this is your mass for bromine. And so when you see Br-81, that should tell you it's bromine. You can look at the periodic table and see that there are 35 protons. And since the mass is 81, then 81 minus 35 also lets you know that there's 46 neutrons. This is Recitation Problem, Chapter 2, Problem 4. And we need to complete the table. Note that the atoms or ions are not necessarily neutral. So if it's not neutral, that's what makes it an ion. It can be a positively charged atom, which would be a cation. And if it's a negatively charged atom, that would be an anion. Okay, so both of those together, cations and anions, make up the terminology ions. Now, in this table, we're going to need to know our formula. N plus, so neutrons plus protons equals our mass. And we need a periodic table. So the mass number, you're going to calculate the mass number. And you're going to calculate this mass number by N plus P equals mass. Okay, so you can go ahead and figure that out. Number of neutrons, you're going to calculate this. Number of neutrons by N plus P equals mass. So that's going to be a calculation. Number of protons, you're going to look at the periodic table, because this doesn't change. If it's selenium, it's always going to have a certain number of protons. And at some points, you might have to do a calculation using N plus P if you're missing the element. And number of electrons, this will depend on the charge of the molecule or the atom. Okay, so this depends on the charge. And the charge is given to you right here. Now when you do the number of electrons, you only change the number of electrons. I'm going to tell you something. Never, ever change the number of protons. Protons are positively charged. So let's start this problem. I've got my periodic table out, and I'm just going to go for the first column. And we got selenium. I'm going to find selenium, and selenium is a non-metal. And selenium has 34 protons. That's always the easy part. So let's put in 34 protons. In fact, just for fun, we'll put protons in red. 34. And that's going to be helpful for our problem here. We have the mass number, 79. So we have the mass number given to us. And so using our formula of neutrons plus protons equals mass, we can solve for N. N plus 34 equals 79. So when you solve for N, 79 minus 34, we get the number 45. So that should be 45. Now, we have number of protons, we have number of neutrons, the number of electrons. The number of electrons depend on your charge. So what's your charge here? Your charge is a -2. So how many protons do you have? You have 34 protons. And protons are positively charged. So you have a negative charge overall. So that means you're going to have 2 more electrons than protons. So that means you are going to have 36 electrons. Because 2 more electrons over protons, the 34 and a 34 is 0 charge. So, and the only thing you can change is the electrons. So if you add 2 more electrons, then you have a -2 charge for your atom. And that would be an anion, okay? Because it'd be negatively charged. Okay, let's go to the next column. We have a mass number of 65, and we're given neutrons 36. So this is where we are. Since we don't have the element, we don't have the number of protons, we're going to have to use this formula. N plus P equals mass. So we put in 36 neutrons plus P equals our mass, 65. So then when you do 65 minus 36, you get 29 protons. 29 protons. So now I'm going to look at the periodic table. So I'm going to look at the periodic table, and I'm going to look for number 29. And when I look for 29, I see copper. Cu. Copper. And the number of electrons. Well, if it's neutral, you're going to have 29 protons positive, so you need 29 electrons, but it's not, is it? The charge here is a +1. So that means we have 1 more proton than we do electrons, but we cannot change those number of protons. So I mean, if you change your number of protons to 29, you change it to 30, now you're talking zinc. You don't have copper anymore. This is the identity of the compound. The only thing you can change are your electrons. So we just need to have 1 less electron than we do protons. So by having 28 electrons, that gives that atom a positive +1 charge. And that would be a cation. Okay, let's look at our last one. Our last one, we have the number of protons. All right, number of protons, 36. I'm going to look at my periodic table. I'm going to find element number 36, and it's krypton. I'm thinking of what superhero? That's right, Superman. Okay, so there's krypton. And the mass number, we're going to have to use our awesome formula here for the nucleus. This is in the nucleus. The neutrons is neutrons plus protons equals mass. So we got 43 neutrons plus 36 protons equals 79. So the mass number is 79. And for the number of electrons, we're given 36. So if we have 36 electrons and 36 protons, the charge is going to be 0. And that is called neutral. And that would be an atom. So we have an anion, we have a cation, and we have an atom. Okay, this is problem chapter 2. Recitation problem 5. And in this problem, we are trying to calculate the average atomic mass of naturally occurring silicon to at least 4 significant figures. So as you can see, what's given to us is 3 different isotopes of silicon. So they have different mass numbers, 28, 29, and 30. So since these are isotopes, they have different numbers of what? That's right, they have different numbers of neutrons. Because it's silicon, I can look at the periodic table and tell you that the proton numbers are 14. So each one of these elements have 14 protons. It makes it silicon. But they have different mass. So it has a different mass. And that's because in the nucleus, where all the mass is, the number of neutrons are different. So as you can tell, silica 28 has 14 neutrons, silica 29 has 15, and silica 30 has 16 neutrons. That's just a little information about isotopes. But this problem is asking for the average atomic mass. And the reason why the average atomic mass is important is when you look at your mass on the periodic table for silica, what do you see? The mass on the periodic table. So look at your periodic table. You see it's 28.0855. Okay? So what that means, to be able to report one mass on the periodic table, the average atomic mass of naturally occurring silica is what's actually reported. So this is what's actually reported on the periodic table. And this exercise teaches you how to calculate it. So the formula that you need to memorize is atomic mass equals the summation of the fraction of isotope N times the mass of isotope N. So when you're dealing with this, you want to convert your percents to decimals. So to do that, you divide by 100. So this will be divided by 100. This number will be divided by 100. This number will be divided by 100 for the fraction of isotope N. N is In this case, silica 28, silica 29, and silica 30. The mass of isotope in, you just basically put that number in the calculation. So, let's look at this and work this problem out. Basically, you want to have the average atomic mass equals, and we're going to sum these up. So you're going to take 27.9769265,327 times, we're going to go ahead and divide that by 100, 0.922297. Multiply that out, plus 28.97649472 times the percent abundance divided by 100, 0.046832, plus the last one, 29.973777022 times the percent abundance divided by 100, 0.030872. Now, when you type that in your calculator, and then a lot of times what I do when I'm taking an exam, I'll just write that answer down because I don't want to make a mistake, and I'll write this answer down, the first answer down. So I write the first answer down on my piece of paper, my scrap paper, and then I take this multiplied by the atomic mass, and then I do the same thing. And then I add all three of those numbers together, and you should get an average atomic mass of 28.0695. And since you want, it says at least 4 significant figures, so how many do we have there? 6 significant figures, but when I see the number 4, I will just go and then I gotta look at the 6. Am I gonna round the 6 up to 7, or am I gonna leave it as 6? So I'm gonna look at the 9. The 9 is 5 or greater, so that means the 6 gets rounded to the 7, and that is my average atomic mass. And that's pretty close. So maybe there's an isotope left out or something like that, but that's pretty close to what's reported on the periodic table. This is problem chapter 2, problem 6, recitation problem 2-6. And this information about the patterns, the periodic law, and the periodic table are on they start on page 61 of your TRO book. And this is section 2.7. So you'll be required to look at a periodic table and classify elements as metals and nonmetals. So looking at your periodic table, you find boron, and these are some of the elements you're required to know, right? On the things to memorize in Canvas, they tell you which elements to memorize, and they're shaded. Okay, so boron, and if you look at boron, and I'm also looking at page 63, you'll find that boron is a metalloid. So that has partial metal characteristics as long as nonmetals. It's kind of in between. Manganese is Mn, and you'll find this in the transition metals. Let's see, what number is manganese? It looks like it's 25, element 25, and this would be a metal because the transition metals are metals. Actually, 2/3 of the periodic table are metals. And the question's asking for nonmetals. Iodine Iodine is one of your halogens. Okay, halogens are group 7A of your periodic table. This actually would be a nonmetal. Okay, halogens are nonmetals. And you go down to the astatine, and that's actually a metalloid. So iodine is a nonmetal. Selenium. If you look for selenium, which is Se, I guess I should be writing these down. This is boron. This is Mn for manganese. Iodine is I. Selenium, Se. You'll notice that this is underneath oxygen and sulfur of the periodic table, group 6A. And this is also a nonmetal. So selenium is a nonmetal. You'll find that silicone is actually a Si, and it is a metalloid. Mercury is in the transition metals, Hg. So silica is Si. Mercury is Hg. It's a transition metal. So by its name, it is a metal. And then carbon. Carbon is C, and carbon is a nonmetal. So your nonmetals are iodide, selenium, and carbon. This is problem 2-7. So problem 2-7, recitation problem. And the question, I've got my periodic table out here. The question is, what is the average mass of a single chlorine atom in grams? So you need to read page 70, section 2.9. So I'm going to turn to page 70, 2.9 here. And it talks about molar mass. Molar mass is grams over mole, or it can be mole over gram. These are your conversion factors we talked about. And now the number that always goes in molar mass with the unit mole is 1. So always put 1 with mole. The grams, the number that you get to go with your grams, comes from the periodic table. So here we're talking about chlorine. And so chlorine is Cl. That's what you have to have memorized. And I see that its average atomic molar mass is 35.45. And I would use all my numbers, 4527 grams of chlorine equals 1 mole. So that's a conversion factor you're going to need. You need to recognize when you need conversion factors. This is also another example of dimensional analysis. We did dimensional analysis back in chapter 1. That was your introduction. So you have grams here. And then they ask, what is the average mass? Now the key here, though, is a single. So what's given to you? This is your given. A single means 1 chlorine atom. That's what's given. And you put that on top, and then you're going to want a number of atoms on bottom, because you have a number of chlorine atoms on bottom. You have 1 chlorine atom on top. To get this to cancel out, you're going to have number of chlorine atom on bottom. Now, what are you trying to find? You want the average mass, and it's going to be in grams. And I've given you a conversion factor here. It's called the molar mass. But you're going to need another conversion factor. And that conversion factor is using Avogadro's number. And that's what is discussed in section 2.9 of your book. Anytime you see number of atoms in the problem, when you see number of particles, it's the number of shoes, number of molecules, number of. You need to think of this conversion factor where you have to, you memorize it. You'll memorize it from using it, but it'll also be supplied to you on your periodic table in case you don't remember it or you want to check it during your test. 6.022 times 10 to the 23rd atoms. So see, that's a number of atoms. This can be chlorine atoms in 1, so equal to 1 mole of chlorine. So Avogadro's number is a lot like the molar mass, where the number 1 always goes with the word mole, and in Avogadro's number, the number 1 is going to go with the unit mole. So what is our conversion factor plan? Remember that? So we're talking about number. So we're taking 1 chlorine atom. And we're going to go from number of atoms to 1 mole of chlorine atoms. Okay, so for 1 mole of chlorine. Once you get to mole, you can go from mole to gram. And the way you do this conversion from mole to gram, you use the molar mass conversion factor, which is right here. 1 mole equals 35.4527 grams of chlorine. Where do we get that? Just always remember, you're going to get that from the periodic table. You don't have to memorize it. You just got to recognize you got to go to the periodic table and get that number. This number, to go from atoms to moles, this is Avogadro's number. And you do sort of have to have that memorized. And it should be on your periodic table, but to recognize when you have to use it. Okay, now we can work out our problem. So I'm going to copy what we originally started with our given, 1 chlorine atom over 1. And then we're going to have Avogadro's number, which is 6.022 times 10 to the 23rd atoms, because that's the number of chlorine in 1 mole of chlorine. And so those numbers are going to cancel out, atom and atom. And then we're going to put mole of chlorine. This is molar mass. And we have 35.4527 grams of chlorine. And I always write down whatever atom or molecule I'm using because it gets really complicated, like the next chapter, when you're changing from chlorine to oxygen or to nitrogen. So it's just a good habit to get into. As you can see here, moles on top and moles on bottom cancels out, and you're left with grams. When you look at the problem says what is the average mass in grams. So that's what you're looking at for a single chlorine atom. Now, so you put this in your calculator. This is where you need to use your TI-30, TI-34 calculator that you're allowed to use on the exam, because you do not want to have to figure out how to do this. On my calculator, I have to use to the EE. And so you want to make sure that your calculator is doing the right thing, because there's this other option on some calculators, like it's a ampersand kind of thing, like that. And if I do, like, if I put in 6.022 and do that to like the 10th, of course that's to a power, right? That's not right. I have to actually hit my second function button, and then I have to hit the EE, and then I put in 23. So I'm going to tell you exactly what I put in. 1, and now this is on bottom, so I'm going to divide. So I hit the divide button. I'm going to put 6.022. I'm going to do my second function, EE, the number 23, and then I'm going to hit equals. And then I'm going to take that times, so I'm just going to hit times 35.4527 equals. And my answer is 5.887197 times 10 to the negative 23rd. And this is grams. I'm going to look at my problem, a single chlorine atom. So it's really hard to tell how many significant figures there are required. So I'm just going to report this to 5.89 times 10 to the negative 23rd grams. Okay, so that is how you do that problem. Okay, this problem is problem chapter 2, recitation problem 8. And the question is asking about how many atoms of tin 124, isotope 124, are present in 27.0 grams of tin. This is kind of interesting. Tin, if I look on the periodic table, I see that its symbol is SN. Has 10 stable isotopes. That's a lot of isotopes. And the one we're interested in is the heaviest, that makes up 5.80% of naturally occurring tin atoms. So what we need to do here, our given is that we're going to start with is 27.0 grams of tin. It's the only unit and with a single number, and that's your question. How many atoms? So that's what we're trying to find, how many atoms. So you remember when I said we're going to have to use Avogadro's number whenever you have number of, so number of atoms, number of particles. So Avogadro's number is always, for 1 mole, you get 6.022 times 10 to the 23rd something. In this case, it is number of atoms of tin 124. So that's one conversion factor. This is dimensional analysis, so our goal right now is to come up with some conversion factors. So that would be a conversion factor we can use because it says how many atoms. Now, this gets us into moles, and we got grams, and we're dealing with an element on the periodic table. So we're also going to have to use a thing called molar mass. So be prepared to use that conversion factor. The key here is to look at the periodic table. You just got to remember to look at the periodic table. Once again, 1 always goes with the unit mole when you're using molar mass. And on the periodic table, you can look up 10, SN, and you can see that the number for 10 is 118.710 grams for 10. And you will find that I always put my element, because when you get later on in working these problems, sometimes you're going from tin to oxygen to carbon, so it's nice to really go ahead and develop good habits. Now, don't forget about this 5.8%, because this right here, 118.710 grams, that is of all of the isotopes. So remember that the periodic table, that average atomic mass, so that takes the percent abundance of the particular isotope into account and sums them all up, multiplies and sums them up. We did a problem like that. So to deal with that, we are going to start with our given. Well, let's do our conversion factor plan, because So it kind of makes it nice. So we start with our given. So we're going to talk about 27.0 grams of tin. We're going to start with that. And then we can go ahead and convert that to 5.80% of the 27 grams. So we're going to have to multiply that. And then we're still in grams. So we're going to go grams to moles. And then we can go from moles to numbers and number of atoms. So to do that, this is Avogadro's number. To go from mole to atom, there. And to go from gram to mole, we're going to have to use the molar mass because we're going from gram to mole. And like I said, we get that off the periodic table. So we start putting these numbers. We start with what are given, 27.0 grams of tin, and we put that over 1. And we don't want that, so we're going to put grams on the bottom of tin. And we need to take into consideration only 5.80% is what we're looking at. So for 100 grams, this is how we do percentage. For 100 grams of the tin, only 5.80 grams of the tin is actually 124. Okay, now we have grams of tin canceled out. We're still at grams of tin, and we're going to do molar mass. So we're going to put grams of tin on the bottom for 1 mole of tin. And we get this from the periodic table, 118.710. Let's come down here. And at this point, 1 grams cancel out, and we're going to put mole on the bottom, and we're going to put Avogadro's number of 6.022 times 10 to the 23rd atoms. And that's what we want. We want atoms. We're at atoms because the mole, put a 1 there because it's Avogadro's number. 1 mole of tin cancels out. So now we get our periodic, we get our calculator, and we type in 27.0 times 5.8 divided by 100 divided by 118.7110 times 6.022 second function EE to the 23rd, and our answer is 7.944 times 10 to the 21 atoms of tin. And we want 3 significant figures, so this is going to be 7.94 times 10 to the 21 tin atoms. So that is a lot of 10 atoms. Continuing on with the last problem of Chapter 2 recitation problems. So this is Chapter 2, problem number 9. It's a part B of the 10 stable isotopes. So here, the 10 stable isotopes. We still are dealing with tin 124 at 5.8% of the natural occurring 10 atoms. Now this question is asking for the total mass of the 10 124 atoms, in the 27 gram sample. So in the 27.0 gram sample of tin, so you got all 10 isotopes, basically for 100 grams of all the 10 isotopes, you have 5.80 grams for tin 124. And so when you do 27 times 5.80 divided by 100, that gives you 1.566 grams of tin 124. And since you have 27.0, that's 3 significant figures. Okay, so we want to report this to 3 significant figures. So that would be 1.57 grams of the tin 124 isotope. So out of 27 grams of sample, 1.57 grams actually belongs to the tin 124 isotope.